Alright, ladies and gentlemen, lesson 7.5, we're going to work on graphing linear equations. We want to be able to identify and then graph them when and if we have them. So linear equation, first of all, is an equation whose solutions fall in a straight line. Okay? So if we take a relationship and we graph it, and we end up either with a straight line itself or a set of dots in a straight line, we have a linear equation. And linear, you'll notice in here, line. So an equation that gives us a straight line. So now, as we go through to graph a linear equation, in this particular case here at the beginning, we're going to use a table. Okay? So we're going to take our equation, y equals 3x plus 4, or minus 4, sorry. And what we're doing here is we're going to take and select some values for x. And when I do it, I try to do some positives and negatives. So I'm going to go from -2 to +2. Because sometimes once we get to 0, our graph does some funky things. So I like to test both sides. We're going to substitute these values into the equation for x. That will give us a y value. And we will then have an ordered pair to graph. So I'm going to take and substitute into the equation here. And all of these values, replacing x with the x's that are given. And then I'll use the order of operations to simplify the expression. Oops, sorry, this is a 3 times 2. Alright, so I'm going to change colors here to do this. Okay, so our order of operations, 3 times -2 is -6, minus 4 is -10. 3 times -1 is -3. -3 minus 4 is -7. 3 times 0 is 0. Minus 4 is -4. 3 times 1 is 3. Minus 4 is -1. 3 times 2 is 6. Minus 4 is 2. And so now I have these ordered pairs, -2, -10, which in this particular case, that doesn't actually fit on my graph. So I should have probably done a little bit different with my graph here, but that's all right. Well, for what we're doing, we'll see what we need to see. -1, -7. To the left one, down 7 would be approximately there. 0, -4. Not going left or right at all. Placing my dot down 4 places. 1, -1. And 2, 2 over 2 up 2. And you'll notice here that those fall in a straight line. Therefore, I do have a linear equation. Just to illustrate that, I'm going to go ahead and use my line tool. And you'll notice straight line. So in this particular case, it is linear. All right, linear. All right, so I have a linear equation. But in other cases, I may not have a linear equation. So we're going to test this -x squared. And again, I'm going to go -2 to +2 as far as my x coordinates. They're not given to me in this case, so I'm going to pick my own. Sometimes they may be given to you. And I'm going to go through and substitute again. So I'm replacing x with -2. And so I end up in this case with a -1 squared, -0 squared, 1 squared, and then negative, and then 2 squared with a negative. So, okay, order of operations again. I multiply before, I raise my exponents before multiplication. So I've got to do this part first. So -2 squared, well, -2 times -2 is 4. Multiply by my negative, and I end up with a negative. So -2, -4 would be down here. -1 squared is 1 times my negative makes that negative. So I have -1, -1. 0 squared is 0 times negative. Well, 0 times negative is just 0. So my ordered pair there is 0, 0. 1 squared is 1 times my negative will make a negative. So to the right 1 and down 1. You'll notice here at this point, this is definitely not linear. It does not fall in a straight line. 2 squared is 4 times my negative gives me a -4. And so to the right 2 and down 4. So there's my graph, and if I were to, and I'll try my best with my graph, and again, with my mouse, not always, should be a smooth curve that does something like that. We get a parabola. So this is definitely not linear. So, all right, then we're also going to talk about rate of change, and your definition for a rate of change is a ratio, a fraction, and you'll notice I've sort of set up, here's the fraction, how the setup would go, comparing the amount of change in a dependent variable to the amount of change in an independent variable. So we're going to set up fractions is what we're going to do for our rates of change, and then if we want to change them to decimals or something, we can. And this is a comparison of the change in the y-coordinates over the change in the x-coordinates. I'm going to show you how we do that right now. So okay, so I have this table, and you'll notice as we move along, the x's and y's are changing. So we're going to compare the amount of changes in our x's and our y's. So what I'm going to do here first is and I'm going to do it this in blue here for my y's, just because I happen to use blue as for my font color. So from 0 to 4 is plus 4. And I'm just going to go across the table here. 4 to 8 is plus 4. 8 to 8 is plus 0. 8 to 6 is minus 2. Now, in this particular case, and you do not have to do it in colors, I'm just doing it to keep things organized in this case. I'm going to do my x's in red. 0 to 1 is plus 1. 1 to 3 is plus 2. It's a change of 2 in the positive direction. 3 to 6 is a plus 3. And 6 to 8 is a plus 2. So now I'm going to go ahead and in each of these cases, I'm going to set up a fraction, okay, a ratio, again a fraction, a ratio is a fraction, at least to begin with, of my change in y over my change in x. So I'm going to go back to blue here, and I put all my changes in y's in the numerator. So this would be 4, I'm just bringing this 4 down, this 0 down, this negative 2 down. That's over my change in x. So I'm going to bring these numbers up here down now. 1, 2, 3, and 2. Okay. Now 4 over 1 is 4. 4 divided by 1. 4 divided by 2 is 2. 2. 0 divided by 3, well, that's 0. And negative 2 divided by 2 is negative 1. So in this particular case, what we're going to do is compare these values here. And if we have if they are all the same, we have what's called constant, which that would be a linear equation. If we don't have the same numbers, it's variable. So in this case, it is definitely variable. It changes. That's sort of the idea of a variable, is it changes. This would be a non-linear situation. So if I were to graph this, EAR, if I were to graph this, I would not get a straight line. Okay? Let's do an example that is a straight line if I were to graph it. So again, my change from 0 to 1 is a plus 1. From 1 to 4 is plus 3. From 4 to 6 is plus 2. From 6 to 7 is plus 1. From 1 to 2 is a plus 1. 2 to 5 is a plus 3. 5 to 7 is a plus 2. 7 to 8 is a plus 1. So if I set up my ratios, my y over x, in this case it's 1 over 1. In this case it's 3 over 3. In this case, it's 2 over 2. Again, y over x. 1 over 1. Well, each of these, 1 divided by 1 is 1. 3 divided by 3 is 1. 2 divided by 2 is 1. 1 divided by 1 is 1. You'll notice all of these 1's are now equal. Therefore, we have constant. And in this case, when we have constant, this would be a linear situation, EAR. This would be a linear situation. It's supposed to be an R. If I were to graph this, this would give me a straight line. All right, so we're going to test now in a physical science application. What we have here is we have an equation that calculates the distance that a thunderstorm is away based on the time between the flash and the sound of the thunder. Okay, and that's what this up here is. I'll let you read that for yourself. So Sandy sees a flash of lightning. There's 5 seconds between the flash and the thunder. Diego sees a flash, 9 seconds elapse, and then he hears the thunder, and so on. So this formula here will calculate how far the storm actually is away based on that difference in seconds between the flash of lightning and the sound of thunder. So what we're going to do, these are a number of seconds here. So we're going to replace the number of seconds, the S, with the number of seconds in each case. So we had 9 seconds apart there. We have 4 seconds apart here. This was Ted's. Okay. Cecilia was 11-second difference between the flash and the sound. And then Masoud here looks like has an 8 seconds difference between the sound, or the flash and the sound. So we're just going to multiply in each of these cases. 5 times 2 is 10, but I have 1 decimal place, so that will be 1 mile away. 9 times 2 is 18, but with 1 decimal place, so 1.8 miles away. 4 times 2 is 8, with 1 decimal place, so 8/10 of a mile away. 2 times 11 is 22, 1 decimal place, so 2 miles away. And 8 times 2 is 16 with my decimal, so 1.6 miles away. So we have these ordered pairs. We have 5, 1, and we're going to graph these. So I'm actually going to flip to my next slide, and I'm going to graph it as I go along. So 5 seconds gave us 1 mile away, and I will plot the point. Oops, sorry, wrong direction. Go back here. 9 seconds gave us 1.8 miles away in distance. Okay, so 1.8. So 9 seconds is there. 2 seconds is up here. 1.8 is approximately right there. So I will go ahead and plot my dot. Okay, let me go back. The next one. 4 seconds gave us 8/10 of a mile. So 4 8/10. Excuse me. 4 8/10 is approximately here. All right, and then we had 11 and 2.2 miles. So 11, 2.2. So 11 seconds would be here. That would be 2, 2.5, 2.2 would be approximately there. And then we have 8 seconds paired with 1.6 miles. Okay, so back to my graph. 8 seconds. 1 would be here, 5, 6/10 would be just above. And again, now we're not exactly perfect. We're having to eyeball some of these things out in the middle. But generally speaking here, do they fall in a straight line? I'm going to use my line tool because I have that ability. I'm going to go back to 0 because obviously if we don't hear any thunder or lightning, it's not going to be any distance away. So you'll notice though that they basically fall in a straight line, and some of it not being in a straight line may be my errors, small little errors in placement. But in this particular case, we are looking at a linear situation. Alright, so that gets us to the end of the section. As always, come see me for your questions. I'm happy to help. Good luck.